All right, welcome to Nested Loops, session 5. We will wrap up session 4, or chapter 4, and then we'll go into chapter 5. Alex, if you will start, just share your screen and
yes,
pick up where we left off.
Cool. Yep, just pulling up the book here. Show my screen. Okay. Can you guys see the screen?
Yeah.
Cool. So we were on this last little bit talking about the law of Demeter. So just going to defining Demeter. She defines it as Demeter restricts the set of objects to which a method may send messages. It prohibits routing a message to a third object via a second object of a different type. Demeter is often paraphrased as only talk to your immediate neighbors or only use one dot. So then we have these couple examples down here. First one being customer.bicycle.wheel.tire. Next one, customer.bicycle.wheel.rotate. And then this last one, hash.keys.sort.join. So these chains are colloquially referred to as train wrecks. Each method name represents a train car, and the dots are connected between them. These trains are indication that you might be violating Demeter. So then she goes through the each example and what if they are, and sort of explains if they are violating and what their violation is. So if looking at the first one, if wheels, so we have customer.bicycle.wheel.tire. If wheel changes tire or rotate, depart may have to change. Trip has nothing to do with wheel, yet changes to wheel might force changes to trip. This is unnecessary. This unnecessarily raises the cost of change. The code is not reasonable. Changing tire or rotate may break something and depart. Because trip is distant and apparently unrelated, the failure will be completely unexpected. This code is not transparent. Trip cannot be reused unless it has access to customer with a bicycle that has a wheel and a tire. This requires a lot of context and is not easily usable. And this pattern of messages will be replicated by others, producing more code with similar problems. This style of code unfortunately breeds itself. It's not exemplary. The first two message chains she goes and say are nearly identical, differing only in one that retrieves a distant attribute tire and the other involves distant behavior rotate. Even experienced designers argue about how firmly Demeter applies to message chains that return attributes. It may be cheapest in your specific case to reach through intermediate objects to retrieve distant attributes. Then it says balance the likelihood and cost of change against the cost of removing the violation. If, for example, you're printing a report of a set of related objects, the most rational strategy may be to explicitly specify the intermediate objects and to change the report if it becomes necessary. Because the risk incurred by Demeter violations is low for stable attributes, it may be the most cost-effective strategy. Yeah, so, she goes pretty much saying, it's you have to weigh against fixing this violation versus if it's going to be returning these attributes that are stable and not likely to change, maybe it's more cost-effective to not go through and fix everything. This one is further down. This part here is I thought interesting. The third message chain, hash.keys.sort.join, is perfectly reasonable, and despite the abundance of dots, may not be a Demeter violation at all. Instead of evaluating this phrase by counting the dots, evaluate it by checking the types of the intermediate objects. So hash.keys returns enumerable. Hash.keys.sort also returns an enumerable. and hash.keys.sort.join returns a string. By this logic, there's a slight demeter violation. However, you can bring yourself to accept that hash.keys.sort.join actually returns an enumerable of strings. All of the intermediate objects have the same type, and there is no demeter violation. If you remove the dots from this line of code, your cost may well go up instead of down. So since all of this chain here, the hash.keys.sort.join, all return, well, they don't technically all return enumerable, but since they're all returning close to the same thing, this is actually pretty efficient, right? And saying that instead, if we were to look at this like, okay, now we have to change hash.keys.sort.join, your cost would go up because you would be writing something that would probably be more complicated than doing this if you wanted to go through a bunch of keys and then pretty much return a string. It would actually be more complicated. Avoiding violations. One common way to remove train wrecks from code is to use delegation to avoid the dots. In object-oriented terms, to delegate a message is to pass it on to another object, often via a wrapper method. The wrapper method encapsulates or hides knowledge that it would otherwise be embodied in the message chain. So there's a number of ways to accomplish delegation. Ruby itself contains delegate.rb and forwardable.rb. And the Ruby on Rails framework includes the delegate method. Each of these exists to make it easy for an object to automatically intercept a message sent to self and to instead send it somewhere else, pretty much. Delegation is tempting as a solution to the demeter problem because it removes the visible evidence of violations. This technique is sometimes useful, but beware, it can result in code that obeys the letter of the law while ignoring its spirit. Using delegation to hide tight coupling is not the same as decoupling the code. Yeah, so pretty much saying is even though you're hiding the problem that your code is really tightly coupled sometimes using using delegation, if your code behind the scenes is still, if you're just pretty much making a wrapper that does essentially the same thing, then it's not actually going to be helpful. Goes on to say, demeter is trying to tell you something and it isn't. Use more delegation, right? Message chains like customer.bicycle.wheel.rotate occur when your design thoughts are unduly influenced by objects you already know. Your familiarity with the public interface of known objects may lead you to string together long message chains and get a distant behavior. Reaching across objects to invoke distant behavior is tantamount to saying, there's some behavior way over there that I need right now, and I know how to get it. The code not only knows what it wants to rotate, but how to navigate through a bunch of intermediate objects to reach the desired behavior. Just a trip earlier knew how mechanic should prepare the bike and was so tightly coupled to mechanic here, the depart method knows how to navigate through a series of objects to make a wheel rotate and therefore is tightly coupled to your overall object structure. This coupling causes all kinds of problems. The most obvious is that it raises the risk that trip will be forced to change because of an unrelated change somewhere else in the message chain. However, there's a problem here that is more serious. When the depart method knows this chain of objects, it binds itself to a very specific implementation and cannot be reused by any other context. Customers must always have bicycles, which in turn must have wheels that rotate. Consider what this message chain would look like if you started out by deciding what depart wants from customer. From a message-based point of view, the obvious answer is customer.ride. The ride method of customers hides implementation details from trip and reduces both its context and dependencies, significantly improving the design. When fast feet changes and begins leading hiking trips, it's much easier to generalize from customer ride to customer depart or customer go than to disentangle the tentacles of this message chain from your application. The train wrecks of demeter violations are clues that there are objects whose public interfaces are lacking. Listening to demeter means paying attention to your point of view. If you shift to a message-based perspective, the messages you find will become public interfaces in the objects they lead you to discover. However, if you're not bound by the shackles of existing domain objects, you'll end up assembling their public interfaces into long message chains and really miss the opportunity to find and construct flexible public interfaces. Yeah, so pretty much to sum up, Demeter is more about making you know, if you're seeing that you have these types of long chains, it might be an indication that that not only you have too much knowledge of your objects well, you should have knowledge of it, but also that your public interfaces might be lacking, and there might be a better way to not have to reach across a bunch of your object chains to get the kind of behavior you desire.
Yeah. It's a lot about coupling. Each dot is knowing something about the sub thing. Like that one, customer bicycle wheel rotate. Like, wow, that's a lot for Trip to know. If you go back to like last session, I was talking about grid managers don't micromanage.
Mm-hmm.
And that's like, you know, I think each dot is more micromanaging. Hey, you tell your thing, do this. Like, no, you just tell the top level thing. That's kind of what the one dot thing is. Ideally, if I deal with other objects, I tell them what to do, and then they manage their thing. I might tell, you know, if it's customer ride. I tell the customer what to ride, and he knows. Actually, it's not ride, but in this case, it's rotate. But, you know, customer rotate, which might go bicycle wheel rotate, right? And then the hash thing is fundamentally a different thing, where not just because each one returns enumerable. I mean, that's a very functional. There's a lot of functional code. It's very dot. That is
right.
on the previous thing being the same thing. You just chain things together. IO is done like in Java that way. It's not, it's a chain, but it's actually decorator wrapped. I just keep passing in the same thing, the same sort of thing to the next thing.
Mm-hmm.
So it's kind of it's a good example of this is when dots aren't bad. Well, it's kind of a different thing. It's not like, hey, hash, ask your string, ask your key to give themselves, and then sort them. And, you know, it's like, it's a chain of stuff, but it's very different than micromanaging like this because they're different objects.
Right. Like the hash, yeah, right. Hash.keys is definitely way more of a functional. I think it was like passing data all through this for like an end result where customer.bicycle.wheel.rotate is just looking for a specific thing, yeah, and not necessarily changing the data as it goes.
Right. The hash.keys you could do like capitalize, you know, and then maybe remove some things, and they all deal with like these lists. Ultimately, here in numeral, right? I could do it, then I could capitalize, then I could remove all things with foo, and then I could join them.
Mm-hmm.
It's the flow of the same object is just, you know, just keep. I'm it's like this flow management of give me your keys, not start them, not capitalize them. Now remove everything that has to do with last week. Now give that to me as a stream of comments. You see how it's, I'm kind of not going to another level of object. Not like customer, give me your bicycle. Bicycle, give me your wheel. Wheel, give me your rotate.
Mm-hmm.
You know, you see what I'm saying? It's not really the same kind of thing. Where I think, you know, like that join thing, it's kind of like munging data. I'm just going through successive phases of the same thing, of the same kind of thing, and a final result. It's a different kind of thing. All right. So, any comments before we move to chapter 5? Okay. Anyone who's talking with the mute, I cannot be heard, so we'll move on to Don.
All right. Let me find my chapter start here. Okay. Can everybody see that okay?
Yeah.
So chapter 5, we're going to discuss reducing costs with duck typing. So just the premise of duck typing is that duck types are public interfaces that are not tied to any specific class themselves. The main idea is if an object quacks like a duck, walks like a duck, then it's a duck. And you can treat them as such in your code. It replaces the costly dependencies on classes with dependencies on messages instead. So that's like the core concept, is that instead of checking to see that the arguments to a method are a particular class, we're going to assume that it implements a certain interface, which is called duck type. See, so our main example of duck typing and understanding duck typing is this example of a mechanic class. Let's see. So maybe just go into the code examples a little bit better. An instance of a mechanic class, an instance of any class, obviously it implements the full public interface of its class. So if you know that an object is type mechanic, you can call whatever methods that mechanic implements, because by its very nature, any object that implements the mechanic public class interface is a mechanic. But you're not limited in Ruby to expecting an object to respond to just one public interface. As the author puts it, the Ruby object is like a party goer at a masquerade ball that can change masks to suit the theme. And that's the idea of duck typing. It's not the idea of what an object is that matters, it's what it does. So focusing on messages instead of classes. So as an example, like just to show how valuable duck typing is, we're going to overlook the duck, which is to look at a code example that does not use duck typing, that instead depends on concrete classes with very specific methods as interfaces. So in our example here, we have a class trip. And to prepare for the trip, we must call the prepare bicycles method on mechanic. And it's very, very specific to mechanic. The mechanic class itself has a public interface prepare bicycles. And we know that by calling that, it's going to prepare bicycles for a trip. So in this code example, you notice that we're not referencing the mechanic by its class name. However, because we're referring to this prepare bicycles, this very specific method to the mechanic, we're still very, very locked into this mechanic class. It's not an explicit dependency on mechanic, but it does depend on receiving an object that responds to prepare bicycles. So we are very, very tied to this mechanic class. So yeah, like as she says, the dependency is so fundamental that it's easy to miss or discount, but nonetheless it exists. The trips prepare method firmly believes that its argument contains a preparer of bicycles. And if we look at the kind of dependency diagram here in figure 5.1, we see that any object that calls the prepare method on trip must then pass a mechanic object that can respond to prepare bicycles, even though we're not referring to the class itself. So as like as this class kind of grows, this trip class becomes more complicated. Referring to these very specific methods or specific classes compounds the problem. So if we go down to the next code example, we had taken this example further by not only adding a mechanic that must prepare for the trip, but a trip coordinator and a driver. And the way this is then implemented in the code example is by doing a select case on the preparer using its class. So now the prepare method takes in a enumerable of preparers and loops over them. And if it's a type of mechanic, it's going to call prepare bicycles. trip coordinator needs to have buy food called on it, and the driver needs to fill up the vehicle with gas and fill up the vehicle with water. And now we see that we're very dependent on these classes. So even though these classes have simple interfaces, the prepare method itself is not very complicated. And most alarmingly, it's referencing each class and different public methods by name. So we write the code because we're blinded by these existing classes. We see that the classes are very simple, and that it's pretty trivial just to see what class the object is and call the appropriate method, because it seems very simple. And so we tend to want to send those messages to prepare bicycle, buy food, gas up, fill water tank explicitly. And we know that those methods provide the behavior that prepare wants. So yeah, the problem with this styling of coding is that it propagates itself. And when you want to add another new preparer or somebody down the line that's working on the code, then they're just going to add a new when branch to the case statement. That's what we tend to do, is just use the structure that's in place. And then you accrue more and more methods like this, where a method knows many class names and sends very specific messages based on the class. The logical endpoint of the programming style is a very stiff and inflexible application. And it eventually becomes easier to rewrite everything rather than change anything. And we'll go down now to 5.2. So looking at the sequence diagram from what we just looked at, is now we've got a very complicated, these very complicated relationships where the trips prepare method must call the very particular method of the mechanic, the coordinator, and the driver. So it's just a complicated dependency diagram now, even though it seems very simple, and we were able to keep mechanic, trip coordinator, and driver looking exactly like they did when we were first introduced to them. We added complexity to the preparer. And that's what duck typing tries to avoid. So what you have to do, though, is you have to find the duck. So to find the duck is you need to identify, you need to recognize that because the trip prepare method serves a single purpose, its arguments should also try to accomplish the single goal that the trips prepare method wants to accomplish. So kind of to illustrate this idea, let's look at what would happen if, let's see. Yeah, so what we're trying to find then with finding the duck is what behavior is is common between all these preparer classes. And so she's kind of demonstrating this with a missing preparer object that we don't actually have. Is what if instead of going through the very specific methods, we're actually going through a preparer interface? It's just like an abstract idea where that preparer interface, if it was implemented as a specific class, would have a very specific common behavior that the trip prepare would expect to see. And look, from this diagram, it doesn't really clean anything up, but when we think about like what the trip prepare method wants, is it wants the preparers to respond to a prepare trip method that's very general. Now, the downside is you have to modify your other classes, the trip coordinator, the driver, and the mechanic. But you want them to behave like preparers, which is our kind of abstract idea of what the duck type is. Even though it doesn't actually exist as a class, we're going to treat it as such by implementing the same method. And then when you look at the diagram that results from that, it's very simple. You don't really care what class each of the objects that was passed to prepare is. You just care that they implement the prepare trip method. And that's how we're finding the duck. So here's the code example, is we added a new method to mechanic, trip coordinator, and driver that is just prepare trip. And that way we don't need to know that prepare trip for mechanic is calling prepare bicycle. We just need to know that it responds to prepare trip. And same thing for the driver. We don't need to know that it gassed up the vehicle, fills a water tank. And we don't need to know that the trip coordinator calls buy food. We just use a common interface. So the consequences of duck typing. The new implementation has a pleasing symmetry that suggests the rightness about the design, but there are consequences that go deeper. So in the initial example, the prepare methods depending on concrete classes, it's really simple to understand that the trips prepare method needs to call very specific methods on each of the other classes. But in the more recent example, prepare depends on the duck type, which is, again, it's not an actual class that's implemented in our code, it's just an idea. And that's harder to understand. So the trade-off here is code that's simple to understand but hard to extend, or harder to understand and easier to extend. And it's this tension between the cost of being concrete or the cost of being abstract. It's fundamental to object-oriented design. So it might take longer to understand the code, but ultimately it's easier with duck typing to extend the code. And there's like a kind of a brief aside about polymorphism and how polymorphism is used. We talk about polymorphism a lot. And what it's really expressing in OOP is the ability of many different objects to respond to the same message. So we typically think, when we think of polymorphism, as inheritance, right? Is using inheritance to ensure that that many different objects can respond to the same message. Duck typing is another way, is that just by implementing the same method name in Ruby, we essentially are getting this polymorphism effect because we can send the same message to any number of objects as long as it responds to it. Okay, so when you're writing code that relies on duck typing, the first step is kind of to identify what code you already have that could take advantage of duck typing, or to discover what ducks actually exist. So to recognize these hidden ducks, we look for really just keywords in our existing code that we're using. The most obvious one is case statements to switch on class. That's what we just looked at, is if you have any kind of code that's changing its behavior based on which class was passed in as an argument, then it's very, very clear that code could take advantage of the duck typing. All the preparers in our case here, they must share something in common. And the idea is to identify what is it that our trip prepare method wants from each of the arguments. And then that results in a duck type. The other is a kind of, or is a, and we see this pretty often, but it's just basically the same thing as the case, that you're determining what the class of the object is and then reacting a certain way. They're no different than using case statement. So it's just another way to rewrite the same code we already saw. So the last one is just maybe not as obvious as a response to. So here's the same code written again, but instead of explicitly referencing classes, we're looking at what methods that the object can respond to. And we're using this response to change which method we call. So this is still very tied to the class. It looks like it's not, but don't be fooled by the removal of explicit class references. It still expects very specific classes. So in any of these three cases, we want to place our trust in duck types as well, or instead of calling these other methods to determine the class, basically. And let's see what, there was a good line here. I'll say the line, but I have it in my notes, is that all of these things indicate that there's a lack of trust in collaborating objects, and they introduce dependencies that make code difficult to change. So instead, you can implement duck types and trust in your ducks. It's effectively saying, I know who you are, because of that I know what you do. It's relying on the behavior of the class or group of objects instead of what their actual identity is. So then we move on to documenting. Obviously, like when you're using lots of duck types, you're treating each of the objects as a preparer, even though preparer doesn't actually exist. It's a public interface that's a concrete part of the design, but a virtual part of the code. And since they're abstract, it makes the duck type less than obvious in the code. And I think basically her statement on testing is, on documenting is that good tests are the best documentation. So as long as your tests are very clear that you're depending on this public interface, then that's good enough documentation for duck types. More complicated thing to move into is that although the preparer ducks provide class-specific versions of the behavior required by their interface, in our example, the method signature is the only thing that they have in common. They share only the interface, not the implementation. But what you might find when you're using duck types is that you'll find classes that implement the duck type, but they have some shared behavior as well. And that's not covered by this chapter, but we'll look at it in chapter 7 on how you share methods between duck types. So this section is about choosing your ducks wisely, which means although you can identify duck types all over the place, you want to be careful that you don't try to do too much. The main difference in like finding a duck type in something like our mechanic in trip preparer, or sorry, our trip coordinator and our driver classes is that those are classes that we maintain as the programmers, not something that's maintained, let's say, in a framework. So in this example, there's a lot of like kind of code to identify the classes being used, whether it's an integer or hash. The major difference between our previous examples and this example is the stability of the classes being checked. When we're depending on the Ruby core classes, those are far more stable than the method we're writing. So the likelihood of those two classes changing in such a way as to force first to change is very, very small. So it's a very safe dependency. Now you could extract a duck type and you could patch the integer and hash code using like some monkey patching. And that's a cool feature of Ruby, but it's actually kind of dangerous to do that because you could actually mess something up down the line with the core classes. So with core classes, it's better just to not worry about duck types and just use them as you normally would. So looking at fear of duck typing, which mainly comes from being used to statically typed languages. So kind of the some of the main ideas in statically typed languages is to define the type of every single variable, every single method parameter, and that way you don't have any type errors. But that's also requires you be very, very explicit with which arguments are allowed to a certain method. And because of that, relying on dynamic typing makes some people uncomfortable. Sometimes it's just because you're not used to it, but a lot of times it's because there's a belief that static typing is more reliable than dynamic typing. So just comparing the two, static and dynamic typing, some of the qualities of static typing are that the compiler unearths type errors at compile time. So if you try to use a type that's not compatible with a method, then the compiler will tell you that you can't use that. Also, by having type information visible in the code, it serves documentation. And then the biggest thing with static type languages is compiled code is fast. That's usually why we decide to use statically typed languages over dynamic ones. And the assumptions of these things is that runtime errors will not occur and, as long as the compiler is performing type checks, runtime type errors, that is. And that, let's see, the programmers will not otherwise understand the code, and they cannot infer an object's type from its context. So it's saying that, like, in dynamic languages, you don't have the types right in front of you. So the idea is that it's harder to understand than statically typed languages, is one assumption that can be made about static languages. And also that applications will be too slow if they don't have compiled code that's optimized to run quickly. However, dynamic languages have these qualities, that the code is interpreted and can be dynamically loaded. There's not a step that you have to do before you can run your code to compile or make the code for a certain platform. The source code is smaller because it doesn't include explicit type information, and metaprogramming is easier. So the idea is that the application development is faster when you're not having to do compile steps to run your code, and that it's easier to understand because you can just look at the context of an object to determine its type, not have to rely on type declarations. So I guess the idea is that there's a smaller amount of code, so it's easier to figure out what's going on. Whereas statically typed programming fans, they think the opposite, that it's you're only able to understand code whenever you have static types present. And then you also like dynamically typed languages if metaprogramming is desirable, which obviously, if you're relying on static types and compiling, metaprogramming is not a feature of those languages. So in order to use duck types, we have to embrace dynamic typing. So it's very true that statically typed code will outperform a dynamically typed implementation in most cases. whenever you can't tune your dynamically typed applications to run fast enough, you usually have to fall back on statically typed and compiled languages. But then there's some subjectivity in the idea that type declarations as documentation are better. Because the more that you experience with dynamic languages, the more you find the type declarations distracting. And in fact, it can be kind of disorienting to see that, whereas statically typed language users might be disoriented by the lack of type information that might be harder to follow. So a lot of it is just like the comfort you have with the language and being able to identify things based on context rather than by explicitly named types that you see. Then on the topic of metaprogramming, people usually feel really strongly one way or the other about metaprogramming. If they care about metaprogramming, then they see it as like a tool to do something really complicated with a really small amount of code, or to have like lots of little clever tricks. But she describes it as kind of a scalpel that is dangerous in the wrong hands, or says that with great power comes great responsibility with metaprogramming. So if you have a really complicated metaprogramming example, then it might do a lot, but it might take longer. It might take longer to understand it than it would have taken just to code it in a more straightforward way. So really the main thing in reference to duck typing that we care about with static versus dynamic languages is that static typing advocates, they think that if you have compile time checking of argument types, then it will completely protect you from accidental type errors. So the argument is that because the compiler can save you from accidental type errors, then if you're not using a compiler, then the type errors will occur, and that they will never occur when you're using static typing. But actually, that's not true, because the compiler does not save you from accidental type errors if you're casting. So once you start allowing variables to be cast into different types, the compiler stops doing such strict checking, and you don't get that protection anyway. So while it seems that duck typing is more dangerous than using a static language, statically typed language with really well-defined types and well-defined interfaces, it's actually not that much safer if you're casting, which is actually done a lot in those languages.
I would Jack, the object-oriented static languages, you can cast, but the more functional languages that are static type, you cannot.
You can't.
And when you talk about the advantage of, well, just the code go, code go, code go, you actually lose a lot of that if you are not running your tests to verify that your dynamic connections are working.
Right.
You have the difference between, let's say, dynamic language programming, that cycle is code, test, go. And in static languages, it's code, compile, go. And in my experience in working in both, it's about the same.
Right.
There are advantages and disadvantages.
Can you get closer to the microphone, Scott?
Oh, yeah. Is this better?
Yes.
Okay. What I'm saying is that I think Sandy's being a little off when she says, oh, it's much more fun to just be able to code and go. But you need to write tests, number one, and then you need to run those tests to see that you're not getting out of sync. An argument on the static languages end is, well, the compilers will keep you from getting careless.
the functional languages. And there are static languages that she's absolutely right about. If you can coerce or cast types, then you don't have a static language, you have a semi-static language.
Right.
And but this is a thoughtful, challenging section to what I've been experiencing in my playing on my own time with static, true static languages. And I would love to kind of run off and see what it would feel like to tackle these kinds of solutions on the static side and come back and say, oh, this is what I found. I don't really know what I'd find, but it's an interesting thing.
And I think another thing she doesn't mention here is that with at least C++ and maybe Java, you actually have like a first-class declaration of interfaces, which are public interfaces, and that in a way is, when we're talking about duck types having a kind of abstract class as an interface that we don't actually implement in Ruby. In C++, you can define an interface and then require the objects that are passed in implement that interface, which is kind of duck typing as well. And it's not exactly the same, but I don't know if you have to cast then once you start calling those, but
I think of this chapter as determine the interfaces that you want to have.
Yes.
Only partially overlapping with what Java calls interface. And so, well, and that's what you're saying. If it quacks like a duck, i.e. it matches the interface I expect, it is. I actually think that Java interfaces are, we talk about like, just because it compiles doesn't mean it works, it just means you have the right types. Which, of course, is the source of a lot of problems in dynamic languages. You make a mistake with the wrong type. So that goes away. But you could have the right type that does the wrong thing. So just because it compiles doesn't mean it works, which is, something that static people kind of imply. So, but anyways, what I like about interfaces is, let's say I have an interface and it implements 3 things. In duck typing, you could maybe only implement one of the 3 things. And you'll be okay for this one part, but then somewhere else you thought it should have some other functionality. You can lose that with duck typing, which I see as a disadvantage. Where
yes,
but I think the primary advantage in dynamic typing and duck typing is you can move faster. The problem in, say, Java is, oh, now I have a new interface. Well, fortunately, Java being static is a refactoring extract interface or something like that one. But you end up having to percolate changes up the hierarchy depending. That can slow you down. Like, oh my God, here's a new interface. And some of these objects implements. Well, yes, IntelliJ and Eclipse will let you extract the interface. But it may not catch everything that you need to do or go up high enough, So that'll slow you down. It's one of those things. I like dynamic because you can move quicker and discover stuff faster. But once you know the answer, it would be great if you could go back and then put that in stone.
Yeah.
So once you know what the actual interface is or should be, it'd be nice to enforce that later. But dynamic lets you move around and reach towards that faster, but it doesn't give you the protection. And the reverse is true. In the static, it will take you longer once you realize, oh crap, I have to do this. And if you're lucky, it's a quick IDE refactoring. If you're unlucky, it's a big thing, and then suddenly you spent half a day doing something you forgot to recode it. So that's kind of where dynamic moves faster. It would be like Matt has been talking about, like conditional static typing in Ruby 3. But that would be great if you can be dynamic until you know what it actually is. You go, oh, this is what it is. Locking it down would be great, and then you won't break that. For the cases that compile checking will help you, which isn't as many cases as people would have you believe.
Yeah, I think that would be really cool. And I think some of the comments here are specific to certain languages, right?
Yeah.
So, like, actually, I think I mentioned it in the first chapter that interfaces, not just like duck typing. That's how I would say it. And you pretty much say and with duck typing, you pretty much define an interface. An interface, it's a more like a Java, C, Sharp, and all that. But let's talk about Java. So Java, you define the interface, and then you implement the interface, all that kind of stuff. It requires you to do a lot more design up front, a lot more thinking up front, and you keep. There's a lot of I would just say ceremony around this type of duck typing. And when you switch to other like functional static languages, this ceremony is not there. So I think like to Scott's point, like certain other languages, they're still static, but they don't have the specific, this is the interface process, and this is like the type of method you can do it, and this is the implementation of that interface. It might be like a good medium between like totally dynamic and Java style static. Now, what you were talking about, yeah, totally. Sorry, I just muted myself. If you can, be dynamic and until you figure out what the interface is, and then go back and kind of fix it. This is okay. This is the type. This is the interface. This is the type of object that it takes. Yeah, that'd be awesome.
Actually, ActionScript lets you do it.
Yeah, no, ActionScript, Clojure lets you do that, and a few different other languages let you do that. There's something I wanted to mention, like when we did the prepare mechanic and all the kind of stuff, and then we switched that and figure out what the duck typing was. There was also like a bit of an example of inversion of dependency, right?
Yeah.
So because like before we say, okay, what was the class? The trip had to know all this other stuff about, and you put like all the dependency on the trip. Now you put the dependency on the mechanic, trip coordinator, and driver to know that you're passing a trip that has bicycle, customers, and vehicle.
Yes.
Dependency inversion. There you go.
Yeah, so it's kind of like they're depending more on the structure of the trip instead of the other way around. So this is making it a lot simpler in the prepare method, but not necessarily overall.
Yeah, I know. Like in some of my code, like I try to sometimes abstract stuff and and I introduce other objects that are very similar. That like kind of makes stuff like a little more complicated. And then afterward, I realized, oh, I should have done it the opposite way, and it would be much easier. So yeah, like every once in a while, like it's just like it pays to look at from a different point of view. I think dependencies is really gets a lot of people many times by surprise.
Yeah, I think my only other comment on this is that whenever she's talking about documentation and just saying good tests are best documentation, I feel like there has to be some other way of that, because I don't know that we're depending on the prepare trip being implemented on all sides, and I don't know if there's a better way to document than just having a test that says, okay, this method exists.
Yeah.
Maybe it's...
on a related notion, so I think it was Uncle Bob. He made some observation. You know, the Ruby and the Rails community, they're pretty agile, friendly communities, if not straight out agile advocating. And so, you know, TDD and testing goes with them. And I think the observation was along the line, you know, dynamic languages like Ruby or communities like Ruby, they test a lot. One, because it's good, but two, because we're dynamic, you should test more. If you want reliable code in dynamic language, you better write more tests. So that's kind of what goes along, and you know, and it's very typical Ruby Rails culture to write lots of tests, and of course, obviously, if you embrace TDD and stuff like that, one you just do it by default, testing and design.
Well, I can agree with that, but like I think to the documentation portion, I think organization of the files, like namespacing, I'm talking, and naming correctly, has is the best documentation.
I think that helps, but where I'm going to is we do it more, and then some people, you know, they look at functional code as, hey, I don't have to test as much because I have no side effects, but then you don't have the test artifact. I don't think the test's a bad thing. One, you know, because it makes explicit the behavior. If you write good tests and if you organize them well, which, you know, I think by design BDD frameworks try to make it so that you organize it in a more sensible way. You don't have to, but the implication is, you know, with context described, you know, that if you actually read the words, you try to at least make it better organized. It's a good thing to write tests to document. That being said, lots of people have lots of tests that no one reads. So it's no guarantee. It's kind of a good thing. It's like, well, we're dynamic, so we have to test. But it's not a bad thing, and if you actually wrote them as with the intention of documentation, it kills two birds with one stone. So it makes up for a weak. It's a strength that makes up for a weakness.
So, okay, I'm gonna mention one more thing. I think tests again are useful also as a design tool, because generally, if the test is hard to write and you need a lot of context to run a simple test, then you definitely have some kind of low dimeter violation someplace, right? Yeah. And then you also mentioned something. If you write a good test, again, writing good test is actually pretty hard, because just like you can, you know, violate low dimeter on the code side, and then you discover on the test side, you can just as well violate low dimeter on the test side and try to test something that are not in that class, right? And this is like I see all the time. Like a really good book. It's the X Unit book. It's a giant on a book, and like we can tackle that another time. It's a long conversation, but I really think like test, yes, provide documentation, provide a lot of stuff. It's a good tool to also help and aid the design, and helps you discover where like your code might have some problems in design wise. But also, in order to be able to do that, you kind of need to be able to learn how to test well, which is, again, it's kind of like chicken and egg problem. Because if you don't know how to code using like good solid design, you probably don't know how to test. In a way that it shows you those problems. Make sense?
Writing, if you write tests first, you become immediately aware of what your dependencies are. And so if you actually write test first code, that helps you decouple stuff. Because if you have no code and you're like, hey, I got one of these, and oh, and this needs this, and it needs that, and it needs this, then quickly you get to figure out, well, how do I inject the dependencies? And then we get to the standard constructions that are registry-based dependency injection thing. But the beauty is, because you haven't written any code, you can see that up front. But yeah, it's an interesting. It's actually good if you have no code and you start writing the test, because you can see those things before you have any baggage. And I think that's one of the great strengths of TDD, assuming you actually know how to write stuff. Related to Diego saying, well, if you can't write solid code, because Sandy made mention something like, well, these TDD gurus, the reason they can do this so quickly is they have a lot of good design knowledge already. So they just think, it's like her solution here with the inversion. That's the first thing I thought about when she showed the code. Oh, that's terrible. Do it like this. And then, 3 pages later, she said, do it like this. But yeah, but, and so I know some people who don't have the experience or the insight in that, they'll struggle and I like that kind of code. Which, if you have the experience, you go, oh no, this is terrible code. It's so brittle. Yeah. Okay. It's 11:06. So I think we'll wrap this up. I think Don's basically done, right? We kind of summarized.
Yep, I think just the summary is that the duck typing creates these virtual types that are defined by what they do instead of who they are. Is separating the behavior from the identity of the classes. Makes it easier to maintain.
All right, which means chapter 6 is next.
Mm-hmm.
And I think we should all agree that one of the person that is missing from here should prepare that, right?
Yeah.
Person is missing today should definitely prepare chapter 6.
Okay, so you're saying we give it to Brett.
Yeah.
Yeah. But today we missed a meeting.
He hasn't prepared anything, right?
No, he hasn't. It's like Andrew did a chapter. The only people who are left, I think, is Scott, Andrew, and I guess Sam. No, Scott, Brett, and Sam. And I go, okay, we can pick that.
All right.
All right, Brett will pick up 6. We'll do 6 in 2 weeks. Hope you enjoyed it. See ya.
All right. Bye. Good job.
Thank you. Bye.
Thanks, Sam.